Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at two example problems that we would normally do in class for how to do pH and Ka of weak acids or Kb and weak bases. How we do those types of like FRQ free response problems. So this matches up with two of them that we'll do in our note packet, so you can take a look at it. It says, what's the pH of a weak acid whose concentration is 0.80 molar and the Ka is 1.75 times 10 to the negative fourth? It says take the answer to 2 sig figs. So there's really no difference here between these and any other IC table weak acid, weak base problem that we've done, other than the fact that we are now including pH. Okay, if we understand what pH is, pH has to do with the hydrogen ion concentration, right? So pH is the negative log of your hydrogen ion concentration. So all we're doing here is solving for that. Okay, if we can end up with this, if we get that, then we could easily find pH. All right. So it says I have a weak acid. So step 1A for any of these problems is to write a dissociation equation. So let's do that. Okay, we've done this a million times so far. Okay, that's what we end up with for our dissociation equation. So that's step 1. It says the concentration of the acid is 0.80 molar. All right, now what I need to find out here is the concentration of hydrogen ion at equilibrium, like at the end, right? So I know it's a weak acid, so it doesn't completely dissociate. So I cannot say that my hydrogen ion concentration is 0.8 molar. If it was a strong acid, I could say that it's a really, really easy problem, but it's not, okay? So I'm going to set up an IC table. That's going to give me a visual of what's going on. So I'm going to have 0.80 molar is my concentration of weak acid, 0 and 0 for H plus and A minus. Simple, plus X for my products, minus X for my HA concentration. My equilibrium equation here, 0.80 minus X, X, and X, okay? Now, remember, we can make an assumption here, my 3 powers of 10 rule. So look, my Ka is 1.75 times 10 to the negative fourth. My initial concentration is 8.0 times 10 to the negative first. So I have a negative 4 and a negative 1. So that's a power of 3 off, which means I can make my assumption. So my equilibrium concentration of acid, in reality, a little less than 0.80, but I could just say it's 0.80 for the sake of solving this problem. All right? And then I still have X and X here. Okay? So I'm going to go to the next slide and continue to solve this because I don't have enough room here. All right? But keep that in mind. My equilibrium value is 0.80 for my HA, X and X for my H plus and A minus. Okay, so let's set up my Ka expression here for the problem, and we'll pick up where we left off on the previous slide. So Ka is equal to my concentration of H plus times A minus over concentration of HA. And let's plug our values in that we know here. So our Ka was 1.75 times 10 to the negative fourth equals X times X over 0.80. All right? Rearrange simple algebra, solve for X. Concentration of X is going to be equal to 0.012 molar, which if you look back on the previous slide or just above on your notes, that is the concentration of H plus. Okay, that's what we want to know here. So that makes perfect sense, right? I mean, the concentration of H plus shouldn't be very big because HA, your weak acid, did very little dissociation to break up into the H plus and the A minus. So both of those, which are X, should have a relatively small concentration, and they do. Now, it's pretty simple. So everything we did so far is nothing new, actually. The question could have been phrased before to find the concentration of hydrogen. Now it's just asking for the pH. So the pH is negative log of your hydrogen concentration. So that's the negative log of 0.012. and it's set around to 2 sig fig, so we're going to get 1.9 for the pH. It should make sense. You have a weak acid, it's still going to be an acidic pH, right? So acidic pHs are closer to 0. So we're good. We have 1.9 for the pH of this. Okay. The next one is dealing with pH and the Kb of basic solutions. So it's not too much more difficult here, but we have to think a little bit. It says, what's the pH of a 0.15 molar solution of NH3, given that the Kb for ammonia is 1.8 times 10 to the negative fifth? So a couple ways to do this. I'll go through one of them, and then I'll show you one other shortcut. So think a little bit. NH3 is a base. Bases are proton acceptors. So we have to write our equation showing that, right? So let's do it. So we have NH3 plus water. It's a proton acceptor. It's accepting a hydrogen from water. We're going to get NH4 plus OH minus. All right? You're going to say, well, how do I find the pH? There's no hydrogen concentration. That's okay. We can work through the hydroxide concentration. In a previous lesson, we learned about the relationship between the hydrogen concentration, hydroxide concentration, and pH, or POH in this case. So we have to go through and figure out that first. All right, so let's do it. So I have a 0.15 molar solution of NH3. We're not going to deal with water. It's a liquid, and liquids aren't included in our IC table or Kb or Ka expressions. 0 and 0. Okay, simple IC table for the most part. Minus x plus x. 0.15 minus x, x, x. Okay, let's rewrite our initial concentration as 1.5 times 10 to the negative first. And this looks like we should use the quadratic, but we don't need to because my exponent on my Kb value is a negative 5. Here, on my initial concentration, it's a negative 1. It's a difference of 4. So that means we can make the assumption. So we're going to have an equilibrium concentration of NH3 at approximately 0.15 molar. Okay. Just like the last problem, I'm going to go to the next slide here, and we're going to use this information to solve, we're going to solve for our hydroxide concentration. We're going to pop it into our Kb expression. So it's really important to know that the Ka is for acids and the Kb is for bases. You can't interchange them, obviously, so just keep that in mind as you're going through and solving these. So Kb is concentration of NH4 plus times OH minus over concentration of NH3. Kb value, 1.8 times 10 to the negative fifth, is x times x over 0.15. All right, do your math. Simple algebra. Concentration of x is 1.6 times 10 to the negative third, and that is the concentration of hydroxide. Right? So if we go back here, x and x, concentration of NH4 plus and the hydroxide ion, OH minus. So that's what we figured out here. Okay, so let's go ahead and use this right here to find our POH. POH is the negative log from our previous lesson, one of our previous lessons. Negative log of the hydroxide concentration. That's negative log 1.6 times 10 to the negative third. And the POH comes out to be 2.8. Okay, so the 2.8 is the POH, which is directly associated with our hydroxide concentration. I want to find the pH. pH is 14 minus the POH. Okay, so we have 14 minus 2.8, so that gives us a pH of 11.2. And we're done. This is a base. NH3 is a base. A base creates hydroxide ion in solution, and it does from our equation here. You can see the hydroxide ion being produced. So the pH should be above 7, right? You shouldn't end up with a pH of 2.8. That's your POH, all right? Obviously, a pH of 11.2 is basic. It's above 7, and that makes sense because we have a basic solution. All right. There is a shortcut for this. Okay, so we could take a look at, I guess it's kind of a shortcut. We could take a look at it. I'm going to erase some of this and show that to you. I'm going to do it up here in the right-hand corner. So make sure you have this. I'm going to erase it real quick. And it's just going to tie in one of the other equations that you guys looked at in a previous lesson. All right, so let me try to get rid of all this here real quick. And it involves KW. All right, so I don't know if anybody remembers that equation or not from one of the previous lessons, but we're going to look at it. So I have the hydroxide concentration here. Instead of solving for POH, what I can do is use this equation. KW is, if you remember, the concentration of H plus times the concentration of OH minus, right? And the KW is 1 times 10 to the negative 14th. 1 times 10 to the negative 14th is the concentration of H plus times the concentration of OH minus, right? Because in water, water is neutral. You would have 1 times 10 to the negative 7th for H plus, and 1 times 10 to the negative 7th for OH minus. And that would give you 1 times 10 to the negative 14th. Well, in this case, we already have our hydroxide concentration. So let's plug it in. 1 times 10 to the negative 14th is your hydrogen concentration times your hydroxide concentration, which we have right here. Solve for H. Simple algebra gives us 6.3 times 10 to the negative 12th for the hydrogen ion concentration. And then just do pH. pH is negative log of the hydrogen concentration, which is negative log of 6.3 times 10 to the negative 12th. And if you plug in your calculator, you get 11.2. Same answer as we just had. All right? So, the problems that you guys have that you were assigned for your homework for today is the next handful of pages. All right? 33, 34, and 35, I think, or 34, 35, 36, something like that. So check the planner. You're going to work through those, and a lot of it has to do with what I just did on these 2 practice problems. That was the whole purpose of doing these with you. So give them your best try. All right? You have a bunch of time to work on those. And if you have any questions, you can look at the posted answer key or let me know next time I see you in class. All right? Thanks, guys.